Okay, welcome to episode 8. In this episode, we'll talk about address decoding. So address decoding is one of the functions of the glue logic, which generically helps the CPU communicate with devices such as memory devices and peripheral devices. The address decoding logic in particular is designed to detect which specific device the CPU wants to communicate with based on the address that the CPU is generating. We'll talk about the background of both glue logic in general and address decoding in particular. We'll design a memory map for our 8-bit microcomputer. We will design the address decoding logic, and then we will see a test circuit and show how generated addresses result in chip-enable signals for our various planned devices. All right, let's get started. All right, so let's start by talking about what glue logic is. And glue logic is simply the logic in the system that helps the CPU communicate with external devices such as memory and peripheral devices. And one important thing to understand about these old 8-bit computers is that the CPU by itself really can't do a whole lot. It needs support chips, peripheral chips, in order to be a complete computer system. And the glue logic is what interfaces the CPU with those chips. So how exactly does the CPU communicate with these chips? So to the CPU, every single device in the system, meaning your memory chips and your peripheral devices, are going to appear as some number of 1 byte, meaning 8-bit memory locations. And so that's how the CPU talks to these devices. It accesses them as collections of these 8-bit storage locations. The 6809 CPU has a 16-bit address space, so which means that every memory location in the overall system is going to be identified by an address that is in the range 0 to 65,535. That is 2 to the 16 possible memory addresses. In hexadecimal notation, that's hex 0000 as the lowest address, and hex FFFF as the highest address. And the way that the CPU, or the way that the software that the CPU is executing actually talks to these devices is quite simple. It simply uses memory access instructions, load instructions, and store instructions to read or write the contents of the memory locations that are available in each device. All right, so since we are going to be talking about things like data values and memory addresses frequently, let's take a brief moment to talk about hexadecimal notation. Hexadecimal just means base 16, so instead of decimal representation base 10, which is what we normally use to write numbers, hexadecimal uses base 16. We'll sometimes abbreviate this as just hex. And so hexadecimal is quite simple. The digits not only are the normal digit values 0 through 9, but they are also the values A through F, and that gives us 16 possible digit values. And what the letters mean, A is 10, B is 11, and so forth, F is 15. The reason that we use hexadecimal notation frequently when talking about computer systems is because each hexadecimal digit represents exactly 16 possibilities, which is exactly 4 bits of information, and that's very useful to have your digits correspond to an exact number of bits. All right, so as a very simple example, let's say that we have the hexadecimal value C7F6. So basically each of these hex digits represents a different power of 16, the ones place, the 16s place, and so forth. And so the way to decode this as a decimal is that it is, the C is 12, so it's 12 times 16 to the third power, 7 times 16 to the second power, the F is 15, so 15 times 16 to the first power, and then the 6, that's the ones place, so that's just 6. And the sum of all of those, the values of all of these hex digits is 51,190. So we will be using hexadecimal notation quite frequently. So let's talk a little bit more about the characteristics of the devices that the CPU will be communicating with. And the main idea is to understand that each of these devices contains some number of 8-bit storage locations. And how many storage locations there are will depend on what type of device we're talking about. Memory devices typically have a larger number of storage locations, perhaps 1K, 2K, up to maybe 32K or 64K. The peripheral devices generally don't need a lot of storage locations. They just need a few to serve as basically control registers for the device. And one important thing to understand about devices in general is that depending on how many storage locations the device has, some number of address signals are required to allow the CPU to select a specific storage location in the device to be accessed. And how many address signals you need depends on how many storage locations there are. So for example, if a device has just 2 storage locations, maybe it's an I/O device that just has 2 registers, you only need a single address input to select between them because one bit of binary information has 2 possible values, so we can select the 2 possible locations. Similarly, if there are 4 storage locations, you need 2 address inputs because 2 bits of information is 4 possibilities. 8 storage locations would mean 3 inputs and so forth. And of course, one important global property for the system as a whole is that the total number of storage locations across all devices in the system can't exceed the size of the CPU's address space, which in the case of the 6809 is 2 to the 16 bytes, 65,536 bytes of data. There are things that you can do, such as bank switching, to sort of work around address space limitations. But in general, at any given time, this is the maximum number of storage locations that the CPU can directly access. Next, let's talk about the different kinds of devices that we will be designing into our system. One very important one is ROM, meaning read-only memory. The important characteristic of a ROM is that because it's read-only, the data and code that is stored in the ROM cannot be modified as the system is running. However, that data is non-volatile, meaning it's going to be preserved, the contents of the ROM are preserved even when the system is powered off. And what that means is ROM is where you can put your firmware code, meaning the code that executes when the system starts up and in general is resident at all times. And so when your system boots up, you want to have your firmware code essentially take over the control of the system, and essentially the firmware ROM should be effectively running the show from a software standpoint. ROMs come in various sizes, 2K and up. The one that I've been using is this WinBond 64K EEPROM. EEPROMs are very nice because in general, ROM devices require special hardware to program. EEPROMs are relatively easy to program and in fact can be programmed with readily available things like Arduinos. Another essential device that you will need in your system is a RAM device. RAM stands for Random Access Memory. And unlike ROM devices, RAM devices are writable, meaning not only can the CPU access and read the data in the RAM device, it can also store data in the RAM device. And this is really useful for any kind of runtime code or data that the system needs to store. So for example, runtime data structures, data that varies over the program execution should be stored in RAM. If you want to have in your system the capability of loading new programs, the new programs should be stored in basically will get transferred into RAM and executed from RAM. The disadvantage of RAM is that it is volatile, so that you're going to lose the contents of the RAM memory when the system is powered off. And RAMs come in various sizes. The ones that I've been using are just the very, very standard 32K static RAM chips that are quite widely available. Another important category of devices are peripheral devices, and there are a variety of types of peripheral devices that provide different functions to the system. Examples include UARTs, which allow serial communication, timer counter chips, which are useful for generating periodic and one-shot timing events. Digital I/O, allowing the system to communicate with external devices like switches and control other kinds of circuits. And in general, peripheral devices are characterized generally by having a relatively small number of storage locations that are used as registers. 2 to 4 is pretty typical. So here's one chip that I've used, which is the 82C55A peripheral expander that gives you 24 general purpose digital inputs and outputs. So how exactly does the CPU communicate with these devices such as memory devices and peripheral devices? So there are three categories of signals that the CPU uses to do this. There are the address bus signals, and those specify which memory location the CPU wants to access. There are the data bus signals, and these are the signals that actually are used to send data to and from the external devices. And then there are the bus control signals, and these essentially synchronize the data transfers between the CPU and the devices. Because the 6809 CPU has a 16-bit address bus, there are 16 individual address signals conveying the 16 bits of the addresses, specifying the memory locations that the CPU wants to access. And the glue logic needs to decode these memory addresses in order to generate a chip-enable signal such that when an address that should be accessing a memory location for a specific device is generated, that device knows that it has been activated and should be ready to talk to the CPU. So that's really what we're going to cover in this video, is how to do the address decoding such that each time an address is generated, we wake up exactly the right device that is going to communicate with the CPU based on which memory location the CPU wants to access. The data bus is used to actually permit transfers of 1 byte of data between the CPU and the device with which the CPU is communicating. And one important thing to understand about the data bus is that it is bidirectional, so that when the CPU is reading data from a device, it is going to configure its data bus pins as inputs because it's reading data that is being provided by another device. But during a memory write, these data bus pins are outputs, meaning that the CPU wants to send data to a device. And that means that the glue logic has to be very careful to ensure that at any given time in the overall system, at most one device is outputting data to the data bus. And we'll see how that works in a lot more detail in the next video. So if the address bus signals indicate which device and which memory location the CPU wants to access, and the data bus lines allow data transfers between the CPU and the device, the bus control signals, which are specifically E and read-write, are used to synchronize the data transfer between the CPU and whatever device the CPU is communicating with. And these indicate both the direction of the transfer and also the timing of the transfer. And we'll see more details about how bus transactions work in the next video. So now we can actually talk about our address decoding logic and how we're going to design it. And we'll start by identifying some requirements. So these are the properties we would like our address decoding logic to have. One requirement is that for every device in the system, we need to be able to generate a chip-enable signal that will enable that particular device when its specific range of addresses is accessed by the CPU. We also need to make sure that for any specific address generated by the CPU, it results in at most one chip enable being asserted. We definitely don't want to turn on two devices that will access the data bus at the same time. That would definitely cause problems. We want to make sure we have a reasonable amount of space devoted to RAM and ROM in the address space. We need to make sure that a ROM is mapped in the high part of the address space, and that is because the 6809 loads its reset vector from the two highest memory locations, so we need to make sure we have a ROM there so we can control what the first program address executed is going to be when the system is powered on. We need to allow for a reasonable number of built-in peripheral devices, things like UARTs and I/O expanders and things like that. We need, or at least we should, try to accommodate some additional expansion in the future. And then finally, as with any digital design problem, it's a good idea to try to minimize the number of integrated circuits that are going to be needed to implement the design. As we create our address decoding logic, what we're really trying to do is to create a system memory map, meaning we want to assign ranges of addresses in the address space that the CPU can access to particular devices in the system. And what's really interesting about this problem is how we assign ranges of addresses to devices is going to considerably affect how easy or hard it is to for the address decoding logic to generate the chip-enabled signals for those devices. And this winds up being a really fun problem because you have to think about, based on where you put the devices in the address space, how you're actually going to generate the chip-enabled signals by decoding particular bits of the address. All right, so let's talk a little bit about the memory map we're going to use. So here is our proposed memory map for our system. In the overall 64K address space that we have available, the first 32K is devoted to RAM. We'll just map a single 32K static RAM device into that part of the address space. RAM is followed by 4K of addresses that are devoted to I/O devices. And then following the I/O region, we have 28K that is devoted to ROM. So that gives us a total in the system of 32K RAM, 28K ROM, and then 4K reserved for I/O. So the purpose of the I/O region is to map in I/O devices. And one thing that we know about I/O devices is that in general, they don't require very many memory locations for their registers. So in general, we kind of want to carve up this I/O region into a lot of little tiny pieces that we can use for individual devices. So here is how we organize the I/O region. The overall 4K I/O region is divided into eight equal-sized chunks of 512 bytes each, and there are enable signals for each of those 8 chunks. And then for the first chunk, we further divide that 512 byte chunk into 16 smaller pieces, which are going to be 32 bytes each. And we will generate enable signals for each of those 16 32 byte size regions. And those will be used for system devices, meaning that those are the peripheral devices that are in some sense built in to the system. And then the other part of the I/O space that is not occupied by the system devices, that essentially becomes available for future expansion. All right, so given this particular memory map, let's think about what the addresses in each of those regions actually look like, because that is going to determine what strategy we are going to use to generate enable signals for the device or devices in each of those regions. Okay, so for our RAM device, that is absolutely the easiest enable to generate. So chip enable signals are active low, typically, meaning we want to generate a low value to turn on the device. So given that for all of the addresses in the region of the address space that are occupied by the RAM, the A15 signal, the most significant bit of the address, is going to be 0 for every single one of those addresses. So the A15 signal, in fact, is trivially a valid chip enable signal for the RAM. So generating the chip enable for the RAM, super easy. Next, let's consider this 4K I/O region that sits right here at the beginning of the high 32K of the address space. And what the addresses in that region of the address space look like is they all have the property that A15 is high and A14, A13, and A12 are all low. So essentially we need to do some combinational logic that will look for this specific pattern of bits in those 4 high address lines, and if they are all in that exact pattern, then we know that the I/O space, the I/O region is being accessed. However, there is going to be further decoding of those addresses into a number of individual chip enable signals that we can connect to particular devices that will assign a smaller part of this overall I/O region to those devices. One thing to note about how the decoding within the I/O region is done is that we are going to be using a very specific device, the 748CT138 3-to-8 decoder, and you will see these devices used very frequently for decoding portions of an address space and generation of chip enable signals. It's really, really useful for that application. So we'll see that when we actually get to the actual design. So finally, we have the ROM. We need to generate a chip enable for the ROM. And essentially, the ROM is mapped into all of the addresses in the high 32K part of the address space that are not part of the I/O region. So basically, the way to generate the chip enable for the ROM is that A15 must be high because all of the addresses that access the ROM have A15 high, but we have to exclude the addresses that are part of the I/O region. And so essentially, if A15 is high, but we know that the I/O region is not being accessed, that means it's an access to the ROM, and the ROM's chip enable should be asserted. All right, so let's start designing our address decoding logic, and the main thing we need to keep track of is what the addresses for each region of memory look like. And what we know is that RAM addresses have A15 set to 0. That's actually sufficient to tell us when we have a RAM address. The I/O addresses have A15 set to 1, but the next 3 bits all set to 0. And then the ROM addresses all have A15 set to 1, but we don't want to enable the ROM if the I/O region is being accessed. All right, so we'll start with the easy problem, which is how to recognize RAM addresses and generate an active low chip enable for RAM. Well, if A15 is 0, we activate the RAM. So that is trivial. We'll just call the A15 line our RAM enable signal. All right, so now that we have the RAM taken care of, let's think about how to recognize I/O addresses. And this is sort of two parts. We need addresses which have A15 high and have A14, A13, and A12 all low. So to recognize this particular pattern of zeros in these three signals, either an OR gate or a NOR gate is going to be very helpful, because that distinguishes between the cases where all of these are 0 versus at least one of these being 1. And the standard 7/4 series logic does not have a 3-input OR gate, but it does have the 7/4-2/7 3 input NOR gate. So what we're going to do is put a 3-input NOR gate on here, and that means that this output is going to go high when A14, A13, and A12 are all low. All right, so next, let's think about how we can generate an active low ROM enable signal. And basically, we want the ROM to be active when A15 is high, but when the I/O region is not being accessed. So, so here's what we're going to do. Okay, so we're going to put a NAND gate here and let the output of the NAND gate be the active low ROM enable signal. And the output of the NAND gate is going to go low whenever both of its inputs are high. So one of the inputs of the NAND will connect to A15. So the output of this NAND can only be low if A15 is high, which is what we want. But we also only want this output to be low if the I/O region is not being accessed. So we know that this signal is going to be high when the I/O region is being accessed. So if we stick an inverter on this output and feed it into the NAND, if the I/O region is not being accessed, then we'll get a low here, a high here, and that in conjunction with A15 being high is going to generate a low signal here. So there is our logic to generate the active low enable for the ROM. All right, so if you were thinking carefully about what we did here with this 3-input NOR gate, you should realize that the output of this NOR gate is a necessary but not sufficient condition to enable any devices in the I/O region, because this the output of this NOR gate only decodes A12, A13, and A14 and does not consider A15 at all, meaning we get potentially a high output here even when A15 is low, and only the RAM should be enabled if A15 is low, meaning we need some additional logic in order to generate any chip enables in the I/O region. Okay, so here is where we are going to bring in a 74138 3-to-8 decoder, and that is going to do two things for us. It will allow us to incorporate A15 into our decoding logic for the I/O region, and it will also provide multiple chip enable outputs for different regions of that 4K section of the address space that is devoted to I/O. So let's see how to do that. All right, so here is how we're going to handle generating chip enables for the I/O region. So here is our 74138 3-to-8 decoder, and what it does is that it will decode these three address signals, which are A9, A10, and A11, and depending on what combination of those is asserted, will generate an active low chip enable on one of these outputs. However, it will only do that if all three of its own enable inputs are asserted, and it has one active high enable and it has two active low enables. And one of the active low enables we just tie to ground, so that's always activated. But the active high enable is connected to A15. So only when A15 is high is it possible for this 138 chip to produce any output. And similarly, this active low chip enable input on the 138 is connected to the output of this inverter, which, as we've seen, is going to be low whenever A12, A13, and A14 are low, meaning that it is possible that an address in the I/O region has been generated. So that gives us precisely what we need to make sure that none of these outputs can be asserted for any address that is outside of the I/O region. And of course, because these outputs are decoding the 3 bits that follow this pattern that indicates addresses in the I/O region, this gives us 8 signals that correspond to the different 512 byte chunks of the 4K I/O region. So this forms the basis of our address decoding logic. We'll see when we look at the schematic some additional support for further decoding the first 512 byte region of the I/O space using additional 138 decoders. So here is the full schematic for the glue logic, and here's the 3-input NOR gate that decodes A12, A13, and A14 to help generate the enables in the I/O region. In our whiteboard schematic, we saw the output of that NOR gate fed to an inverter. Here we're actually using another 3-input NOR gate as an inverter. That's a really common and useful trick if you want to save devices to use fewer chips, is to reuse NAND gates or NOR gates as inverters if you need an inverter. Here's the NAND gate that generates the ROM enable signal. A15, of course, is our RAM enable signal. Here's the 138 decoder that divides our 4K I/O region into 8 512 byte chunks, and the first enable in that region, corresponding to the lowest 512 bytes of that 4K I/O region, is further fed into 2 additional 138 decoders along with the address lines A5, A6, A7, and A8, and essentially this first 512 byte region is further decoded into 16 32-byte regions, and so that gives us the capability to add 16 sort of built-in peripheral devices, each of which can have up to 32 registers, which is more than we need. So that this gives us lots of room for built-in devices, and then these additional enables for the other chunks of the I/O region allow for future expansion. All right, so here is our test circuit. These chips here are the actual glue logic. There's our NAND gates, 3-input NOR gates, top level 138 that decodes the overall I/O region, and then the 2 supplemental 138s that generate the individual chip enables in the first 512 bytes of the I/O region. And then the LEDs down here turn on when a chip enable signal is being generated. So right now, this is the RAM enable that is being generated. This LED represents the ROM chip enable, and then these 16 LEDs are the individual I/O device chip enables. And the 7-segment displays here show the address that we're generating using these dip switches. And essentially, the dip switches allow us to pretend to be the CPU in order to generate an address to see how the glue logic responds by enabling an appropriate chip enable signal. All right, so let's generate some addresses and see what chip enables get asserted. So right now the address is 0 and the RAM enable is asserted. And what you can notice is that regardless of what address bits are set to 1, as long as A15 is low, we're still going to be generating a RAM enable signal because all of those addresses correspond to the RAM device. However, when A15 goes high, now we're in the upper 32K of the address space. And as long as we are above the 4K I/O region, in other words, as long as the address is hex 9000 or above, now we're generating a ROM address, and the ROM's chip enable is going to be asserted. All right, so address is 8000 to 9000. That's the 4K I/O region that we use for I/O devices. And the first 512 bytes of that region from 8000 to 81FF, that is what is decoded by these 2 supplemental 138 decoders into the 16 individual system chip enables. And so what we find is that as long as we are generating an address that is that is below 8200, we are selecting one of these 16 chip enables. And depending on which pattern of dip switches we select here, we could select any of these 16. What we find then is that the moment the address gets to be 8200 or higher within that I/O region, we are now no longer generating one of these chip enables, and essentially that means that the region from 8200 to 9000 is available for future expansion. Okay, so that's it for this video. In the next video, we will do the second part of the glue logic, which is to look at how the bus control signals work and how we can use them to essentially tell the various devices in the system when reads and writes are happening. And we will look at memory transactions in some reasonable amount of detail and perhaps capture some traces on the logic analyzer or oscilloscope. And, who knows, maybe we'll even execute some code from the ROM chip because we're very close to that point. Okay, I will see you next time.